You don't have to worry about mispronouncing my name because
Did I say it right?
my ancestors already did that for me. Yeah. No. Right, yeah, thank you very much. Now, I was originally scheduled to be the 28th speaker of the day, starting at 6 o'clock, but then I got upgraded when I came in this morning, and I thought, because I specifically set my talk up to be the last talk of the day and be entertaining, but then I thought, no, I'll keep it as it was, because I'm still wanting to entertain you this afternoon. Yeah, so it's all in the title there, and of course in the abstract there's more information. And I'm all about looking at rocks close up and at different scales. And I'd like to acknowledge my co-authors from various places: Brucker, Germany, the Geological Survey of Finland, and the Open University, and especially the chap there that's highlighted in green, Mahesh. So as geologists, petrologists, we very much value rocks that have come from the moon, either human collected samples such as this one, or rocks that arrive on our planet from the moon. This sample actually is a very special one. It's one of the samples that Neil Armstrong picked up. And some of you might know this particular sample. But look how small it is. This is the problem. We are looking at very small fragments of hand-collected samples. That's because we don't want to destroy the whole sample. We're very much wanting to preserve it. And yet, of course, we can make fantastic observations, even on very small pieces of rock. These images are optical images, plane polarized light and cross polarized light. And even though the colors on that screen don't look very impressive, hopefully those of you who can see the side screens are really enjoying the birefringent colors of the basalt. And in this case, it's the pyroxene. But again, this is still a very small area of rock. It's only 30 microns thick. And is it more of a specimen than a sample? In other words, is it really telling us everything that we can perhaps get from these samples? It's also destructive. We've had to actually cut the rock, grind it, polish it. Now, last year I turned up here and started to promote this idea of multi-scale, multimodal, and multi-dimensional imaging of lunar rocks. And we used an example where we'd been working on an active volcano in the Canary Islands, in fact, the island of La Palma. The image on the left-hand side was taken by an astronaut out of the window of the space station as they were orbiting the erupting volcano. So that's one level of observation. And you can see the difference between the ash cloud and the gas plume. So that's impressive. Then, of course, we come down to Earth and we observe the volcano erupting. We collect the samples, we then bring them back to the lab, and we can go all the way down to very, very fine scale. And the reason why we can do this is that we have different technologies that allow us to bridge these different scales of observation. Now, lunar meteorites, and this is what I spoke about last year, and I'm going to speak again today about lunar meteorites. They're very special rock samples from the moon because, as we know, they've arrived here somehow. They've bounced off the surface due to some event on the moon, but we don't know where they've come from. But they may well have sampled an area of the moon that, of course, humans have not, or even robots. And this is one example that I'd just like to review again. This is a breccia sample. This is a thick slice, and these are the two sides of the thick slice, just an optical image, nothing special. But we can actually, without making a thin section, we can actually take those special thick slices and put them into something called a scanning micro-XRF. And this creates beautiful images. Hopefully you can see the better colors on the screen. And we can see everything that's in that rock in terms of the chemistry, the minerals, the textures, the grain size. And if we know what we're doing, we can actually take this elemental information and convert it into mineral information. And so instead of this just being a chemical map, which it starts off as, it becomes a mineral map of the entire sample. And we have not damaged it in any way, shape or form. We've just put it into an instrument and called a scanning micro-XRF and imaged it. And this leads us then to a sort of workflow which we're developing. multi-scale, multi-dimensional, multimodal, that allows us to look at things really quickly without damaging them at different scales. And then we can zoom in and actually say, right, that area there is the one we really need to go off now and do microprobe or laser ablation or make a thin section. And then, of course, at that point, we start to damage the sample. But we've triaged all our samples to the point where we know exactly where the areas of interest are greatest. But there's this thing called this scanning micro-XRF. So let me just quickly review what this thing is, because some of you may never have heard of it. And I got into this because, yes, I know this is a bit of keep with me here, but this is a device that was originally developed for the art industry. And like many technologies, CT scanning was for biological investigations of the human body. Here we have a technology that was designed originally for tracking fake artwork. Now, this is a painting that's particularly special to me because it was painted by a Finnish artist some years ago, but because he's painting the moon here. And I was very interested to know what sort of paint was he using to paint the moon, the snow, and the rocks. And so we took it out the frame, put it into this scanning micro-XRF, which uses an X-ray beam, but it doesn't damage the painting in any way. The picture moves underneath the X-ray beam, collects samples of spectra on a predetermined grid, and then creates an image. And that image looks a bit like this. And you can do it for any element in the periodic table that the machine can detect. Here I'm just showing zinc. And you can see that the artist in this case was using zinc white to paint the moon. And this was very encouraging because titanium white hadn't been invented when that painting was made. So we know this is a genuine piece of art, but I wasn't doing that. I was actually mainly doing it. I wanted to know what sort of metals and minerals the artist had used in his paint. And because you can use lead. Lead in this case was used to highlight the rocks. Then you can do combinations of elements, and then you start to create your own art. This is chemical art, effectively. But the point I'm trying to make here is that this device, which is non-destructive, can do large area scanning, can give you chemical information. That chemical information can be made into mineral information. And we know for sure now that Pekka Halonen, the artist, used cadmium white and zinc white to create the moon in his lovely painting. So we can apply the same principles then to large pieces of moon rock that have either come to us from the moon or we've collected and brought them back. And here we have a very nice breccia again that we've just been investigating. This particular sample is special because the original people that described it thought that there may well be some hydrothermal alteration within the sample, and that may have occurred once it had arrived on Earth, but it might actually be indicative that there was something happening on the moon. So my challenge here that Mahesh set me was, could I scan this entire sample without damaging it? Yes. Can I find minerals that might have been hydrothermally altered? Possibly. And could this add to the debate that this sample might have insights into perhaps hydrothermal alteration on the moon? Or is it all just something that happened when it arrived on Earth? So we have a glorious image, which, again, please refer to the screens of the entire image here, the entire sample. And every pixel then and every color that you see there is a different mineral, as defined by a different chemical composition. Look at the scale bar there. This is much, much bigger than a thin section, those of you who are geologists and petrologists. And we can see everything that's going on in there, and we can start to quantify it. But what's most impressive is that I found at one point in this sample an aggregate or a clot or a class of olivine-bearing grains. And I thought, this is the one I must go for, because this could be an example where we might find information about whether there's been any hydrothermal alteration, because olivine is very unstable, as we know, in the presence of aqueous solutions. So there we go. We have a class then that's effectively made up of little olivine grains as found by the scanning micro-XRF. And there is a limit to this device because you can see that the right-hand image is a bit fuzzy, but that's just simply telling us that, yeah, it's reached the end of its resolution. So what you then do is you take this same sample that you have not damaged, you have not carbon coated, you put it into an SEM as is, And this is a cut surface, not a polished surface. So we put it into a large chamber SEM under low vacuum, therefore you don't get any charging. And I zoomed in on one particular olivine that I like the fancy of, and I fancied it. There we go. I fancied it simply because this olivine had a black fracture running through it. That black fracture had a mineral inside it that could well have been something like an altered phase. So if we go and have a look at that area there, I don't know how well you can see it, but again, refer to the screens. We zoom in, and if we were to put an EDS, an electron beam on any one of those areas that's got this dark area, not only was that olivine and the XRF had identified it correctly, but that infill there, that fracture infill or alteration feature is actually, we think, serpentine group minerals. So if I go back to the idea here, this is an olivine then that has been hydrothermally altered. It's started to break down to serpentine, perfectly normal behavior. But did it happen on the moon or did it happen on Earth? That's what we still are wanting to establish. But the point now is that we know exactly where to go in this sample to follow this up with higher resolution imagery and other devices. We haven't damaged the sample in any way. We've got information really up front. And I've just been given the 5-minute warning. So I just want to round off and say that that same thin section that you saw earlier on that was made from the sample that Neil Armstrong picked up is also portrayed here in this image, which again looks ghastly, but if you look at the monitors, you can see it looks lovely. It's basically saying again that even this little fragment, you can start to see things that you probably didn't appreciate in the optical image. And in fact, there's some very, very interesting zoning in some of these pyroxenes, which again, after 55 years, we'd still like to go and investigate because they're capturing the origin of the moon and what happened at that point. And I think I'd just like to end then by saying, please, yes, still let's keep looking at rocks. Let's look at rocks with the right devices. Let's share our experiences and our technologies. And if anyone's interested in following up, I'm more than happy to help out with any petrological or mineralogical examinations. And here are my details. And I'd like to thank you for listening. Thank you. Oh, sorry.
Thank you, Alan. That was great. I could listen to that all day. Wow.
Thank you.
Any questions? You must, yes. Can we
have one at
bring?
the back then.
Okay.
Yeah.
Hello, hi, Abby
Hello.
Freeman at JPL. This is really interesting.
Thank you.
Pardon if I missed it. What is the spatial resolution of the scanning XRF? And then how long does a scan take? Like minutes, hours, or
Yes.
days?
Yes, no, I always get asked this question. So it's an X-ray beam. It's not an electron beam. It's not an ion beam. It's not a laser beam. It's an X-ray beam. And it's focused to about 20 microns when it hits the sample. And most people will be horrified at that and say, oh dear, you can't see anything or do anything with a 20 micron beam. But actually, you can. And what happens is it's not like an SEM where it steps across and collects a spectrum, steps across. The X-ray beam is bathing the sample all the time with X-rays. And it's the software that's actually chopping up the spectrum to the resolution that you've selected. So even though you have a 20 micron beam hitting the sample, you can still do 1 micron steps across the rock. So you actually get around all the problems that you have often with an SEM. But also, because it's an X-ray beam, it sees most of the periodic table. And of course, you can't do that with an electron beam. So if, for example, you can map strontium in feldspars. Possibly you could do that with an SEM, but it's painful. But it also excites the slightly heavier energy lines, which again are not visible to a normal SEM. Now, in terms of time, it's like any pixelated technology. The more pixels you put on the, or more measurement points you have, the longer it takes. But this is fully automated. It runs overnight, over the weekend. And that image of Neil Armstrong's thin section, well, the thin section was made from his sample, was taking probably about 2 to 3 hours. But you can let it run, you know, for many, many hours if you want, or you can speed it up and go really, really fast. So it's completely up to you. It's operator dependent. There's another question.
John Fisher, University of Manchester.
Hello, yeah.
Really cool pictures. So I was just wondering, I guess it's following on a bit from the last question there. Would it be possible to then take it further and try and get quantitative numbers out of it?
Oh, yes,
Is
yes,
it
of
not
course.
possible?
Because I was the 28th speaker, I just wanted pictures. And even though the projection doesn't do it justice, but hopefully so on the screens, yes, everything you could ever want from it. So the modal proportions, the grain size, the associations of minerals one to the other,
I guess I was,
porosity, fractures, everything can be quantified.
well, I
Yes.
guess I was thinking more about, can you get like the sort of oxide weight percent for
Yes.
different mineral phases?
Yes, of
and all that
course,
kind stuff, yeah.
because it's a chemical-based identification. And what's great from a mineralogical point of view, because I'm a mineralogist, is that that's how we classify minerals, based on their chemistry primarily. I mean, other than crystallography, it's really the composition of the mineral that we're after. So this is not an inferred technique, it's an absolute technique. And it only goes wrong when, of course, you've got two minerals that have the same composition, but different crystallography. And that's when, of course, you have to switch to something else. And that's why I'm not today proclaiming that we found olivine on the moon that's hydrothermally altered and it happened on the moon, because we need to follow up on this. But we know now where to go and how to do it. And hopefully next year we'll come back with some great news. But thank you for the question.
Thank you.
I'm afraid we don't have time for, yeah.
I was one online.
Oh, okay, very, very quickly. Okay, there is a, at the bottom one from Josh Snape? No? This one, no? Barbara Cohen, all right.
Please.
What is the uncertainty on the quantification of the elements in the XRF?
Right. Again, this is not a microprobe. It's not competing with a microprobe. And a microprobe is really still the only way to properly quantify the composition of a mineral. But, you know, I mean, you can see things obviously at the percent level, and you get an indication for the trace elements, but it's EDS. And I know some people don't believe in EDS analysis. It has to be wavelength, but actually the detectors on these technologies nowadays are so good that EDS analysis, you know, is very accurate. So I can't give you the absolute numbers, but I'll contact Barbara and let her know. Yeah, but thank you.